Monica Aidelsburger for this afternoon's session, and she'll be telling us about the quantum simulation of lattice gauge theories with neutral atoms and optical lattices. Please take it away.
All right. Okay. Thank you very much, and thank you very much for having me here. It's a pleasure. As I already mentioned, it's my first time in Cambridge, so I'm very happy to have finally made it. This is an experiment talk, so I would like to spend the first 15 minutes or so advertising and introducing the platform before I actually talk about lattice gauge theories. And the main motivation, I think, will be to convince you that we are doing analog quantum simulation experiments, but now there's a lot of control. We add digital control elements to these platforms. So they are actually quite powerful. They are not universal quantum devices, but we have quite a lot of capabilities that I also would like to share with you. Okay, so very basic, in a nutshell, what we do. We have laser beams that we interfere to generate some light pattern, and then the atoms see this as a potential energy landscape, and they move in this periodic potential. And the easiest thing you can do is take two laser beams, interfere them, counter-propagating, and then the spacing between neighboring sites is half of the wavelength of the laser beam. So that means that the length scale of this is micrometer, so half a micrometer typically, which depending on where you come from, compared to condensed matter systems, is really large. Compared to Rydberg atom arrays for quantum computing, it's really small. So this is on the order of half a micron, which is basically nice because you can see dynamics, so atoms can hop between neighboring sites, but it's large enough that you can still optically resolve it. So then you can generate these types of images, which I will explain in a second, where you can see each individual atom that is trapped in this potential. So this allows us to simulate Hubbard-type models, which in the simplest form, so here for a Bose-Hubbard system, has a kinetic energy term, so J is the hopping matrix element between nearest neighbor sites, and U is the on-site Hubbard interaction energy. And then you can play different types of tricks to make this more complicated, add nearest neighbor interactions, make these terms tunable, imprint artificial gauge fields. So you can play tricks to make this Hamiltonian more complicated, but that's what you get naturally if you just load cold atoms into that type of periodic potential. Okay, so how do we generate these images? So essentially, our experiments look a bit like that. So that's a schematic drawing. We have a vacuum chamber, which is, in our case, fully made of glass. So that's a glass cell. It's extremely tiny. The top window is like 3 centimeters in diameter. And the atoms are trapped in the center of this glass cell. It's a standing wave trap, so it has a square lattice geometry, and out of plane then there's an additional confinement. So typically we study 2-dimensional systems. There are ideas also to extend it to 3D, but 2D is like our natural way to study these systems, because it allows us to take high imaging objectives in order to resolve each individual atom and also manipulate the individual atoms. So what we do to generate these images is we freeze all the dynamics after the experiment and then scatter near resonant photons. And here each individual dot is one cesium atom, and we scatter a few thousand photons in order to take that picture. Okay, so what actually happens during this process is that we project our quantum many-body wave function onto configuration bases. And then in order to get properties from this snapshot, we sample many of these configurations and then compute mean quantities like the mean occupation. But there's more information in these images. We can look at fluctuations, we can look at subsystem fluctuations, density-density correlations. So there's a lot of information in these images, but in each experimental cycle, we get one of these results, okay? And then we sample from this. And then the sample is that, and we start all over again. All right, so now there are many different examples that I could explain to you in order to convince you that these systems are very powerful. I selected some of the topics that I'm working on since a few years that I think are very interesting. So we are working on studying topological phases of matter, where we imprint artificial Aharonov-Bohm phases onto our system in order to make the Hamiltonian topologically non-trivial. What we are really good at in these platforms is to study dynamics, because we can prepare initial states with high fidelity and then just let time evolution run according to a certain Hamiltonian that we can implement. So this is in contrast to ground state physics. So I have not added this example here, but a big topic is of course studying the low temperature phase diagram of the Fermi-Hubbard model. This would be the opposite regime where we try to go to lower and lower temperatures. And then the topic that I will speak more about is lattice gauge theory. So I will give you an introduction of like how to think about these models in our system and recent results. We have worked on implementing diamond models in our lattice.
Can I ask a question?
Yeah.
So about the previous slide, so where you showed these different configurations, right? The one before this, with the wave function. Yeah. Is it possible to arrange a geometry in such a way that you peak around, that you predominantly get one such configuration?
So I will tell you more about this because that's more or less in this realm of engineering kinetic constraints, and then indeed some of the configurations turn out to be blocked. Okay. More, yeah, I should say, please just interrupt me at any time. There's no problem. Also, if we don't make it through all the slides, that's perfectly fine. Okay, so let me zoom out a little bit, just to basically give you an idea of what we are trying to do these days. So I mentioned that we are working with analog quantum simulators. So we are implementing a Hamiltonian, which is based on the microscopic interactions between the particles that we can tune. But then what we have access to is this Hamiltonian dynamics. So there's a large body of work in engineering different types of Hamiltonians so that we can get access to different types of physics. Because it's a specialized device that can give you access to properties of certain Hamiltonians, but it's not universal. The positive thing or aspect is that we have very large system sizes, a few thousand particles typically, and very long coherence times. So we can study these systems for thousands of tunneling times or interaction times. So they are really powerful these days and go beyond what we can access with classical numerical techniques, but they are not universal. And all the way on the other side is where I would put digital quantum computing, where everything is gate-based. And specifically, we do this with Rydberg atom arrays, where we are really trying to build a universal device that is fully programmable. Now, we in principle know how to do error correction, but it hasn't really been demonstrated yet. So this is the dream, but we are just not there yet. And so the idea for this whole space in between is, well, let's just keep our very powerful systems over here and make them a little more programmable, just as much as we need in order to extract more interesting observables, engineer different types of Hamiltonians. That's essentially the idea. And so at some point I call this computational quantum simulation. You also hear hybrid digital analog computation. Everything falls into this category, essentially. And before I start talking about lattice gauge theories, I wanted to give you a few more concrete examples of what that means. And I'll do that very briefly because I don't have too much time, but let's focus on one aspect. So I highlighted this one block here, which is work where we have started to access nearest neighbor orbital operators. And essentially, the idea is, if you go back to this slide that I showed you in the beginning, here we project onto occupation basis. So we can get access to density-density correlators, subsystem number fluctuations, and all these kinds of quantities. But you don't really have any information about phases. And now if you play with these local rotations in the form of nearest neighbor double wells, you can access some information about the relative phase. Not all of it, but it gives you additional information. And this is how it works. So instead of just projecting this and taking the snapshot, we introduce an additional time evolution step. So we cut the tunnel coupling on every other bond and on every bond here. So we have only dynamics between two nearest neighbor sites. And we can fully control how that looks like. And that's a very simple system, so I can understand this in a two-level basis. I have the left-hand side and the right-hand side of the double well, and I can put it on a Bloch sphere. And if we look at this in a two-level system basis, it's very simple. So I can either have like a symmetrically coupled double well, and in the spin language or in the two-level system language, this would be a sigma x operator. I can introduce an energy offset between the neighboring sites, and this implements a sigma z operator. Okay, so combined, I have this Hamiltonian that I can fully control, which means I can implement any arbitrary operation for this type of two-level system. So if I put it on a Bloch sphere, I have the left-hand side here on the pole, the right-hand side on the pole, and then if I express my operator in the original Hubbard language, then the sigma x operator is kinetic energy. It's just a tunnel coupling between neighboring sites. Typically, we measure the expectation value of sigma z, that's the density, or in this case, like the imbalance, occupation on the left-hand side minus the right-hand side. If I express this, I get my typical A dagger A Hubbard operators for the kinetic energy, and I get access to local currents as well. So really just by introducing this additional small time evolution step, I can rotate my measurement basis. That's one way to look at it. Or I can also use it to prepare different types of initial states, because typically what we do in order to study quench dynamics, for instance, let me go back to this slide again, is we prepare like one of these configurations, we prepare like a product state of placing the particles somewhere in the lattice. But now I can use these additional operators, the nearest neighbor rotations, in order to imprint currents or phases in my initial state before I start my quench experiment or the time evolution. So this gives us a lot of flexibility, and on top of that, as you can see, because we have the combination of the two, we can implement arbitrary rotations, and this data is just a potential energy difference between neighboring sites. And because we have these high-resolution imaging objectives, I can project potentials into the atomic plane, which means I can selectively rotate some of the bonds while leaving the others unaffected. And that now gives you access to more complex correlators between kinetic energy and density, between currents and kinetic energy. So you get access to a large number of observables that previously you could not easily measure. And to demonstrate this, we have taken this measurement. So what you see here is essentially experimental data where we have generated a large array of atoms and resolved the local currents between neighboring bonds. So each one of these black dots is one lattice site. And instead of measuring occupations, which in this case would be just uniform, we implemented these double whale rotations in order to get access to the current distribution. So this is a snapshot, well, an averaged snapshot of the actual current distribution that we generated in this system. Now, I don't have the time to explain to you how we actually generated this state. Just so much to tell you that in each one of these isolated plaquettes, there are two strongly interacting bosonic particles, and we have generated this artificial Aharonov-Bohm phase to thread a flux, magnetic flux through the plaquette, and if you prepare the ground state, you get these circulating currents in each one of these plaquettes. And now we have a technique to actually resolve the current distribution in that system. And this is specifically interesting for topological physics, because often the information is not directly accessible in the density, but in other non-trivial quantities. And here's one example that we have studied.
Excuse me.
Yeah.
So in the previous slide, so you started your system with the product state and then evolved your Hamiltonian, or what is the...
So in this case, indeed. So in this case, actually there are two particles on each one of these plaquettes. Initially, they are in a mod insulating type configuration, and then we slowly ramp into the ground state of this plaquette in the presence of the magnetic field.
Once we in the ground state.
Yes, so we prepare the ground state in each one of these plaquettes. And on the next slide, we couple these together into a ladder geometry, which is quite interesting. The phase diagram of this flux ladder is very similar to the one of a type 2 superconductor. So we actually find chiral currents around the edges of this ladder system, and the density is completely uniform. So this is one example where you really would like to have access to other types of observables that are not just on-site occupations. And so we have done this for a strongly interacting system. Here the Hubbard interaction divided by the tunnel coupling is on the order of 11, which is hardcore for a ladder system. It's bosonic particles, and we measure the chiral current, which is the current around the edges of that ladder system. And in this case, we have about 25 particles, and this phase diagram essentially resembles the one of a type 2 superconductor. Here in the Meissner regime, you have like a nice chiral current around the edges, and in the vortex regime, those break up into current vortices, like vortices in a current profile. Here it's plotted as a function of the coupling ratio K over J. It's a little more intuitive if you plot it as a function of the artificial flux that is piercing the lattice system. Then you see that there's a Meissner phase, the carrier current increases as a function of the flux, it hits a critical value, and then the field starts to penetrate the lattice system, and then vortices appear in the current profile. So this has been a very important result in the community, because we've managed to reach this with very low temperatures, or relatively low temperatures. And this is one of the possibilities to get into the fractional quantum Hall regime, which so far has been very challenging for our community. We have been stuck at 2 interacting particles so far. So we are quite proud that we managed to push this to 24, which for condensed matter people is not a lot of particles. For us, it's actually quite a lot of particles. Okay, so this is one example for how we can use these additional control capabilities to access different types of observables. The other one that I wanted to mention is related to also readout observables. And here we looked at subsystem return probabilities. And this is motivated by the idea that a lot of the studies that we do is quench dynamics, for instance, in the context of thermalization. And theoretically, a quantity that is very useful to describe these dynamics, or also chaotic dynamics, is the Low-Schmidt echo. And Low-Schmidt echoes are very, very challenging to measure. Here, we essentially play a trick and measure subsystem return probabilities that are defined in the following way. So we have an initial state psi 0, which in this case is just a product state. So we place the particles at certain positions in the lattice. In this case, it's 1, 0, 1, 0, 1, 0, so it's a charge density wave of one particle on every other side. We don't actually measure this state, because otherwise it would be destroyed. So we just prepare it with very high fidelity. Then we let time evolve. So what we measure is psi of t. And then we measure subsystem bit string probabilities. Essentially, we look at fingerprints of this initial state that reappears in the time evolved state. So what you see here, this P is a projector onto the initial configuration. So it's 1 whenever you find the pattern in your initial state. And then we take the product of all of these and average over different subsystem strings. Okay, so now these types of quantities, I think, will become very, very important, because even if you find a protocol that allows you to measure the Low-Schmidt echo, the global Low-Schmidt echo, it's exponentially small in the number of particles. And I mentioned before that now we routinely work with 50 by 50 two-dimensional systems. So there's just no way, even if you have a good protocol, to access this quantity. And so what is quite interesting is to look at what this subsystem return probability can teach you about the many-body system. And just to mention 2 examples, and one of the 2 I will explain in a little more detail, but we have looked at it to measure dynamical quantum phase transitions. And I will show it to you on the next slide, or like the following few slides, that it can actually reveal higher order correlation functions, genuine higher order correlation functions. And it is a quantitative measure of the accessible Hilbert space dimension in the thermodynamic limit. I will explain in a second what I mean by that. And in this publication, actually the data that we show, there's no theory curve whatsoever in the whole paper, which is exactly, I think, the type of quantity that we want for actually using our quantum simulation experiments to also find interesting physics. Because we are really beyond the simple benchmark experiments where we want to compare to theory. We really try now to establish these quantum simulation devices as a real synthetic matter, quantum matter, where we can also probe new systems. So we need observables that tell us and teach us something about the system without knowing in advance what to look for. So the type of experiments I already mentioned that we do is we look at quench dynamics. So we prepare an initial state psi 0, quench, let time evolve according to an Hamiltonian H, and then, for instance, ask if the system thermalizes or not. And there are these well-studied extreme regimes of thermalization where the system behaves in an ergodic way. And there's the many-body localized regime where in the presence of disorder the system fails to thermalize. We have now looked for a number of publications, a number of years in this region in between, where you find non-ergodic behavior without the need of disorder. And specifically, we looked at Hilbert space fragmentation, where you find that your system, if you look at the global conserved quantities of your system, like particle number, magnetization, dipole moment, they are conserved. So we know that our Hilbert space has these different symmetry sectors. I can label my state according to these quantum numbers, and then you get these different symmetry blocks. But in the fragmented regime, you find that this block actually shatters further into exponentially many of these disconnected fragments. They are called Krylov subspaces, and these lead to non-ergodicity without disorder, and it's heavily initial state dependent. So if I prepare certain initial state psi 0 that has a quantum number according to this block, it depends on the overlap with each one of these individual fragments, how the dynamics looks like. So depending on what initial state I prepare, the relaxation dynamics can differ vastly depending on the initial state configuration. So this is known as Hilbert space fragmentation. And for a number of years, this has been studied in tilted Hubbard lattices, which is very easy to realize experimentally. We just take our normal Hubbard system and apply this linear tilt. Now this model conserves center of mass or dipole moment, but it exhibits Hilbert space fragmentation. And the intuitive picture is a little bit related to the question that you had asked in the beginning. We engineer kinetic constraints. So this is one way to get to such a fragmented regime. So I've drawn here two cartoon pictures of models that give you fragmentation in the perturbative limit. So here you see a configuration where the dynamics is essentially restricted to correlated hopping processes, where two particles can hop onto the central site, but individual particles cannot move alone. Okay, so the dynamics is highly constrained. And if you perturbatively derive an effective Hamiltonian in the limit where delta over J is very, very large, you find that this Hamiltonian is fragmented. There's another example where you have a resonance, where you indeed go to a regime where a particle can hop on another one that is two sites away. Again, that's a correlated two-particle hopping processes, which highly constrains the dynamics of the system. Now, it's not intuitive just by looking at these processes to see if a model is fragmented or not. And in fact, we have implemented a different one in our experiment where there's no tilt, but it's a staggered on-site potential, and you connect only two nearest neighbors onto a doublon. So essentially 1, 1 is connected to 2, 0. And if you now do the limit delta over J going to infinity, you end up with a very, very simple effective Hamiltonian that really only has these correlated hopping terms. So two nearest neighbors are connected to a doublon, and that's all that can happen. And now this one is actually very intuitive to see that there are different fragments that emerge. Because if you now think about the initial state that I gave you before, which is like 1, 0, 1, 0, 1, 0, obviously this one is stuck. Like it has no way to undergo any dynamics. But if you prepare a different initial state, for instance, like all zeros and then all ones, a domain wall state, it has a lot of dynamics that it can undergo. Just one hint that there may be something interesting going on. And so these are the two different states that we actually looked at in our experiment. Now, one other comment that I would like to make, typically, all these relaxation or thermalization experiments have in the past worked in the following way. You prepare some initial state, like this one, a charge density wave. And if you want to address the question if the system thermalizes or not, you look for a memory of this initial state. So you measure the amplitude of this charge density wave and watch it decay as a function of time. If it vanishes, you say it's thermal. If it doesn't, there's some signature of localization. But it's not very satisfying in terms of an experimental quantity, specifically in the case of fragmentation, because now you need to redefine what thermalization actually means. So let's just say you prepare an initial state in this block. If it thermalizes, it means it thermalizes within this fragment. But this does not necessarily mean that the amplitude of this charge density wave fully washes out. you don't really know. You're not averaging over all the microstates in the whole Hilbert space anymore, so it can have non-trivial structure. So you don't actually really know what's going on. You just see that maybe there's something non-trivial. And so the subsystem return probability, you can actually connect to the effective Hilbert space dimension. And I wanted to be fast on this part, so I didn't include all the slides, but the picture is very simple. So you have a large chain, in our case it's about 50 sites, and you look at the subsystem quantity. And now it's important that the subsystem size is small compared to the total system size. So it's like a small system that is embedded in a bigger bath. And if you are assuming that this initial state thermalizes within its fragment, then the bit string probability will go down as 1 over the effective dimension of the Hilbert space. And you can show mathematically that this subsystem return probability is connected to the thermodynamic entropy. So you can essentially, by measuring the slope of the log of the subsystem return probability, which we do here, so this is as a function of the subsystem size, from this slope, extract the effective dimension of the Hilbert space the system has access to in the thermodynamic limit. So this dashed line over here is a slope of 2, which would mean if you have a system that can only be 0 or 1 locally, you would get exactly that. Now, in the ergodic case, we find something that is larger than this slope, which is because we have bosons and they can also form doublons. So the local Hilbert space dimension is a little bit larger. But in the ergodic case, there's no initial state dependence. They both have exactly the same slope. If you go to the fragmented case and we compare this initial charge density wave and the domain wall, we see that they behave very, very differently. And indeed, that's what you would expect for the fragmented case. This one down here, the charge density wave, ideally is completely stuck. We see a finite slope due to the fact that our initial state is not perfect. I mentioned that we don't actually measure the initial state. We have some finite entropy in the initial state, so this is what you see in the slope. And then the domain wall has a much higher slope because it's in the largest fragment of that system. So this is now compared to theory. You can actually do combinatorics and work out the dimension of the Hilbert space in the domain wall case, which is about 1.39, and the charge density wave is ideally 0. Right, sorry. So this is essentially, I think, what is nice about this, this quantity, because it did allow us to measure this fragment dimension quantitatively without having to put in the model. And I'm emphasizing this because the fragmented Hamiltonians that have been studied so far have all been derived in the perturbative regime. We don't actually fully understand why they work so well, because we typically study these models far away from where the perturbative limit actually applies. And it's very, very difficult to take into account like all the higher order terms and work out how they affect the dynamics. And here you can just simply ask the experiment, like how many states do you have access to? And you can do that as a function of time. So here we picked about 300 tunneling times. Eventually all this goes away. Eventually the system will become ergodic and all the fragments are connected. And you can also use this quantity and analyze it spatially. In principle, you could look at domains and analyze spatially how the thermalization dynamics evolves. So I think that's a quite interesting quantity, and it also works in 2 dimensions. Now, the last thing that I wanted to mention in terms of tools that I think will open up a lot of new possibilities is the sign reversal of the Hamiltonian or time reversal dynamics. And we have started playing with this using our local control, and I just want to share one very preliminary result which we have done with hardcore bosons. Here what you see is space. So we measure here the dynamics density-density correlations after a quench into a homogeneous lattice system, sorry for this mistake down here, as a function of time up to 10 milliseconds, which is a few tunneling times. And at this point here, we switch the sign of the Hamiltonian, and you see that the density correlations refocus after twice this evolution time. So now we can really come up with protocols that then also allow us to study out-of-time order correlators and so on, where we apply local perturbations. Okay, questions? No?
So
Yes.
You got to in the earlier part of your talk, you said when you constructed these plaquettes that you had 2 atomic wafers.
We had 2 atoms, 2 strongly interacting atoms.
The same kind, right? So
Same kind, no internal degree of freedom, no spin, no color. Yes?
How come you don't get exactly the same thing when you go back at some loss in the system, or?
Okay, so here's where we change the sign. So I think up to here, it works quite well. It doesn't work here, so this is a fairly large distance of 10, well, plus minus 10 lattice sites. And what you don't change is residual potential inhomogeneities. So this only changes the sign of the tunnel coupling J, but not if you have any potential energy term that also appears in your Hamiltonian due to corrugations at the bottom of your potential or something like that. So residual disorder will make it disappear at some point. Okay, so then I will talk about lattice gauge theories as promised. And here, let me just briefly highlight the type of Hamiltonians that we want to implement and how we think about these problems. So in addition to our Hubbard type Hamiltonian, where we have our psi-dagger matter operators that describe hopping between neighboring sites, we now, in addition, want to have these parallel transporters or link operators that live in between the vertices of our lattice. And now, in principle, that looks very similar to Hubbard terms, but it has been quite challenging, actually, to implement these models. And these ideas are very old, so they are decades old, but it has just been very difficult to realize. And the reason for that is that what we usually have is global symmetries, but no local symmetries. And if you want to implement Gauss' law, we really need that because we want to encode matter. And if matter hops around in the lattice, then the gauge field on the link needs to change in a very specific way. It has to respect the local symmetry of the model that we are trying to implement. And this is essentially, in a nutshell, all that we have been trying to do for many decades. And these constraint dynamics or correlated hopping processes that I mentioned previously are actually one way to get there. So you could think about this very simple cartoon where you encode a positron and an electron on the vertices of your lattice. And you implement a field configuration in the background. And now if you manage to encode the process in a correlated hopping such that every other site is a matter site, which here would be one particle here, empty in the middle, connects to forming a doublon on the middle site, you can map this onto a simplified U1 lattice gauge theory, where you have then this positron electron annihilation process or pair creation process in the system. And before I explain to you the model that we have implemented, I want to zoom out a little bit just to explain where the field started. Because originally, I think everybody was trying to do U1 lattice gauge theories in 1D. The paradigmatic model that we had tried to implement also in our quantum simulation experiments. So the processes have the following form. So we have the nearest neighbor tunneling, here with strength W, and the matter gauge coupling between psi and the parallel transporter U. And in addition, we have this fermion doubling term, so we put the particles on the vertices of the lattice, and we have positrons and electrons separated on even and odd sides of this matter lattice. So we can give it a mass m, and then in principle we can also introduce an energy for the electric field. Okay, so then this I probably don't have to explain. So they have to fulfill certain commutation relations. And we can define the local charge according to the occupation on the matter sites. This is due to the staggering for the positrons and electrons. So we can map our lattice onto a cartoon configuration like this. We have our matter sites that we separate into even and odd, and then we have the fields in between. Now you can see there's already a challenge once you reach that point, because you realize that the electric field is not bounded. It's an infinite dimensional Hilbert space, which is something that we really don't like, because we are working with particles where we engineer the microscopic interaction, so we can add a flavor to it, but it's usually finite. And this brings us to quantum link models. And I think these days, most of us are actually implementing quantum link models, so we truncate this local Hilbert space. And okay, this is Gauss' law, decouples into the physical subsectors. And here, maybe one additional word, so these are the local generators, which we would like to be conserved in our model. And now the picture that we typically have in mind is, now if you implement this local constraint, also your Hilbert space decomposes into these different subsectors. And you could try to realize now a gauge theory that allows you to study all of them according to these local symmetries. But you can also find ways to implement these types of Hamiltonians or models, and then they resemble the physics in only one of these subsectors. It's a very specific charge sector that you can realize. So you don't reproduce the full spectrum of your gauge theory, but only a subset of it. And as long as it is energetically separated from the rest, or you have some other symmetry constraint, you can still faithfully study the physics of that specific subsector.
So when you said that you cut off basically the gauge fields, do you make it cyclic or do you just cut it off?
Yeah, so let me go there. So this is actually mapping it to spins. So the link operator becomes a spin raising or lowering operator, and the electric field is the Z component of the spin. So it's finite. What we typically do is spin 1/2. So it's really just
it's not cyclic. It's not that that you can jump from one to one thing. If you keep on raising that, so you annihilate the state.
Yes. But it's still U1 symmetric, the model. But it's kind of weird, right? And it's actually, I think, very interesting to look at the properties of all of these quantum link models and these implementations, because we do find phenomena of more complicated gauge theories like string breaking, confinement, and so on. But of course, it's a different realization. It does not have the same degrees of freedom. And like you mentioned, Jürgen, so they have done a lot of work in taking the continuum limit and everything and so on. In all of these quantum link model representations, this is not taken into account. This doesn't exist.
They do classical statistical simulations. That's why they can do it.
Right, and so this is essentially the starting point, I think, where now a lot of results have come out. Okay, so this is a basic pair annihilation creation process. The first experiments have actually been realized with ion traps in a digital quantum simulation, and like this is a faithful representation of the experiment. This was indeed only done with 4 ions, simulating 4 time evolution steps of this pair annihilation or particle-antiparticle creation process. And I think already this simulation required more than 200 gates for this little calculation with 4 ions. And then in 2022, it was realized with 6 ions. Now, this even also made use of a trick. It's not the full quantum link model where you have matter and gauge degrees of freedom. It's in 1D, so you don't actually have to implement both. It's highly constrained, so you can integrate one out. You could either integrate out the gauge field or you can integrate out the matter field. In this case, they implemented the one where they integrate out the gauge field. This requires exotic long-range interactions between spins, which you can realize in an ion trap system. Now, with neutral atoms in optical lattices, there has been a number of results, also from Heidelberg, and this experiment is from John-Wei Pan, or was from John-Wei Pan. And here the idea is very similar to the constraint models that I've introduced in the beginning. So it's this optical lattice potential where you play with potential energy offsets in order to constrain the dynamics of the system. Okay, so what do you see here? So you have this nearest neighbor hopping term J. There's a Hubbard onside term U. And again, you tune it to resonance such that a 101 is coupled to 020. And this additional linear potential is there in order to suppress second-order hopping of just a single particle. You just don't want that a single particle undergoes any dynamics. There should only be this correlated two-particle hopping processes. And if you look at these constraint dynamics, you can come up with the following mapping that allows you to implement a spin 1/2 quantum link model with U1 symmetry. And again, you see a similar strategy. So there's matter sites that are either odd or even, so antiparticle and particle sites. And then you have this map that tells you how to interpret your state. So if the antiparticle site is occupied, you interpret it as an electron. If the particle site is occupied, you interpret it as a positron. And the fields are encoded either in an empty site or a doubly occupied site. That's all that can happen. Link sites are either 0 or 2. Matter sites are either 1 or 0. And then you see that if you have a configuration where you have a 1, 0, 1, so you have an electron and a positron and nothing in the middle, the correlated hopping connects you to a doublon, which changes the sign of the electric field on the link. So this is this particle-antiparticle pair creation and annihilation process. That is the basic dynamics of this U1 quantum link model. And if you go back to the Hubbard operators, it essentially looks like this. So here we have this spin raising operator. So that's the basic matter gauge coupling. Here in a spin 1/2 truncation. And in the bosonic operators, it looks like this. So you annihilate two bosons that are separated by two sides, and you generate two bosons in the middle. So this has been used to produce a number of different results, also to study thermalization. There's a theta angle that allows you to study a phase transition in this model as well. And there's one additional result that came out more recently from Marcus Greiner's group, where they implemented a Z2 symmetric lattice gauge theory with dipolar atoms. Yes?
Are all these one-dimensional simulations done on open boundary conditions?
We always have open boundary conditions. Just due to the nature of the system, right? At some point we have the edges of, like we implement like a repulsive box potential, and that restricts where the particles can go. You can actually also put things on a ring. Like in 1D, you could implement periodic boundary conditions. In 2D, I wouldn't know how to do it. And this is a similar idea, actually also for the implementation with 1D Rydberg atom arrays, where they implement the PXP model. The idea is you can also realize these constraints with nearest neighbor interactions. So for instance, in a Rydberg atom array, if you have the Rydberg blockade interaction large enough, so that there can be only a Rydberg atom on every other side, this introduces a constraint, like a local constraint that you can interpret as a gauge theory. So I think that's the main examples. There's another example from the Heidelberg group down here, where they actually tried to really use a symmetry in the Hamiltonian to implement a gauge theory where the symmetry is essentially given by the internal atomic level structure. So there are spin-changing collisions, but the symmetry is built in. It's not perturbative. Okay, so now we have been working on implementing such a gauge theory in 2 dimensions. And this is a collaboration with our theory friends at TU. Actually, Melissa is one of the driving forces behind this work. She's in a group of Michael Knapp and Frank Pollmann and Clemens. Actually, these two are in Harvard at the moment. Well, actually, for the foreseeable future, I guess. Okay, so especially Rydberg atom arrays, because they're very programmable, have triggered a lot of new results in that direction. So here's one from the Chiara paper where they looked at string breaking. Here is an implementation with Google on superconducting qubits, where they also looked at string dynamics. Again, here for Rydberg atoms, you see that the constraint is due to the Rydberg blockade. So again, what you see here, this is a honeycomb geometry. And here, this red circle here indicates the Rydberg blockade radius. And then you can map the excitation to a Rydberg state into like a dimer. And you see that here, if you put the black one as an excited state, the red atom, then these neighboring white ones cannot be excited. So if you replace this one with a dimer, the black site, you see that each vertex can only be connected to one dimer and one dimer only if you implement that constraint correctly. And then you end up with a dimer model that is U1 symmetric. And now we do this with neutral atoms in a two-dimensional lattice. And the implementation works as follows. It's actually very similar to what I've told you already on the previous slides. The isolator process where two atoms that are separated by one side in the middle are connected and they can form a doublon. And now we find a clever way to engineer energy penalties in order to isolate a leap lattice structure. So this in principle is a two-dimensional lattice, but if you look at these isolated processes that I mentioned where these two sides can form a doublon in the center, and you do the same thing along the perpendicular direction where the central side can never be occupied, then you have this leap lattice type structure. And okay, so I already explained this. We penalize this process, we allow for this correlated hopping, and then we add an additional linear potential in order to also make this one energetically costly, that one particle can hop in a second order process to a site that is two sites away. So we detune this in energy, and then this allows us to effectively realize such a monomer dimer model. So now we just forget about all of these energy penalties. This is the effective Hamiltonian that we get in perturbation theory, and the mapping is very simple on the vertices. If we have a particle, that's a monomer. If there's a correlated hopping process and a dimer forms in the middle, this is then corresponding to a site that is occupied by two particles. So you get this basic coupling mechanism that connects two monomers to one dimer. And if you go away from resonance, it adds a mass to the dimer state. And of course, this is a second order hopping process, so it's small, but our system is coherent enough that we can see these dynamics. And then the local Gauss law becomes very simple. It's essentially that each vertex can only be connected to one dimer and one dimer only, or there's a monomer on the vertex, and that's all. Okay, so the Gauss law becomes very simple. We can count the number of monomers, the number of dimers, and this number is conserved. If we subtract 1, it has to be equal to 0. So this is one of our typical initial states that we prepare. So we start with an all monomer state. So we put the particles on these green sides. You see that there are some defects, there are some dimers, but this is an actual snapshot of the initial state. Typically, we work with about 900 lattice sites. So that's a fairly large system, and our initial state fidelity for this very first try was 87% monomers, and there's about 1% dimer. And so the first thing that we can do is check if Gauss' law is actually fulfilled. So we prepare this initial state and then just quench onto resonance where the monomers and dimers can resonantly form. Okay, so this is maybe a little more technical. So then what you see here is we can just track the monomer occupation, we can track the dimer occupation, we see these oscillations, and then from this pattern analysis, we can essentially extract the overlap with the Gauss law sector and how well it is fulfilled. And this is what you see here in the staggered superlattice without this additional tilt, where it does not implement the gauge theory. We see that the overlap with the Gauss law sector goes down, while in the case where we add this additional linear tilt that protects us and respects the symmetry, then we see that there's basically no evolution outside of the Gauss law sector. So this implements the theory very well. And now the question is, what can we do with this model? And so this is actually quite interesting. Now, if we look at this axis as a function of the mass, if we make the mass very negative, then this monomer initial state is actually the ground state of the system. This is where we start. For the Gauss law dynamics, we quenched onto resonance. And in this case, of course, what happens is that many of these dimers can form, right? We have a lot of dynamics. But now if we increase the mass to very large values, we should connect to a dimer state. So energetically, this one is favored. But of course, it's not unique. There's a degeneracy. There are exponentially many of these dimer coverings that have all the same energy. So the question is, starting from this initial state and ramping across the resonance, what do you get? Like, what's the final state that you expect to connect to? And is there any superposition of the dimer coverings, or do you pick one? And of course, if you would be able to connect to a superposition of dimer coverings, this would be very interesting because it's directly related to the RK wave function. And so we have started to look into this. And numerically, we actually do find for small systems that there is a ramp time that connects you to the RK wave function, or to the RK point. So let me explain the spectrum a little bit. So here's the monomer state, that's the unique ground state. Over here we have these exponentially many degenerate dimer states. And then here you see that this is the energy penalty, this is actually the mass that you would need to pay in order to form a dimer. And here it's the energy penalty that you would need in order to split a dimer into two monomers. Okay, so now what happens if we ramp from very negative to positive is that these states come down. They have to. So we, at a finite ramp time, we non-adiabatically ramp across these manifold of states, and we try to be adiabatic with respect to this branch. And if you do that in a certain time window, you actually connect to an RK-type state of finite size. So the correlation length will be finite. You won't get like an extended RK wave function. But there is a ramp window where you can be non-adiabatic with respect to these states, but adiabatic with respect to those.
So this RK wave function has very specific phases for the superposition. So how do you know that? So why would these phases be exactly the ones that you will get?
Right. So this, what we looked at, was in numerics. So we can check if it's equal phase, equal weight superposition of the dimer coverings. And you indeed see that for a certain ramp window, they all align, like all the phases align. If you do it too slowly, then they don't. They start to spread out, and the phases are not uniform anymore. And what is funny is that actually this becomes worse the larger plaquette interaction would be. So in our case, the plaquette interaction is very, very tiny. But if you make it larger, then it's more challenging to be in that regime where you get the RK point, the RK wave function. But it's a very good question, like how do you even show that in experiments, right? And that's very, very hard. And we're still working on this. We started just ramping into that phase. Like there are very simple checks that we can do. We can look at the dimer covering. We can look at how homogeneous the distribution of different dimer coverings is. Actually here, you see that if we look at the patterns that are fulfilled by Gauss' law, the 2 dimer coverings, 3 dimer coverings, they're all very homogeneous. Here you see some structure, which is actually due to a drift in our experiment that we understand now. So these peaks, they're actually the columnar states. So we had a tilt in our lattice, and so this favored some configurations over others. Of course, this is a very fine-tuned point, so the experiment needs to be very stable in order to reach all these homogeneous coverings. Just a short comment before I move on to explain how we want to detect phases. We can look at the dimer-dimer correlations, and even just the classical physics I think is quite interesting because it connects to spin ice. So we have actually looked at the properties of these dimer-dimer correlations, and you can find like pinch points and all these kinds of things people look at in spin ice. So there's also the mapping to electric fields. But we have been trying to come up with a sequence that would allow us to detect the phases between the coverings. And this is a bit related to these local control operations that I mentioned previously. Just now they have to be a little more complicated, which makes it hard. So what we want to detect ideally would be that, right? So this is an equal weight, equal phase superposition of all the dimer coverings. Now this we cannot detect, like that's out of scope, this we cannot do. But we can try to see like local coherences. And we had the idea that we can look for plaquette coherences. We can try to see signatures of this dimer configuration having a coherent superposition with this dimer configuration. And you can come up with local rotations that allow you to detect such a superposition. So what we can do is we can apply a pi pulse along X. Now what does that mean? That means we split one dimer and prepare this monomer state. Then we can imprint a phase between the two components, which is just the mass between the dimer and the monomer. So it's detuned from resonance. And then we apply another pi/2 pulse along Y, which mixes these two states. And then we measure the probability of finding this monomer configuration, which should then oscillate as a function of the phase that we imprint. So this is a bit like a Ramsey sequence, just a little bit more complicated. And we have implemented the first few ingredients. So essentially what we do, this is our lattice. We project repulsive potentials into the atomic plane to detune these sites so that we can implement these pi pulses between 3 neighboring sites. And then you see these nice oscillations. So we can actually indeed manipulate X and Y axis with respect to each other. And we have also demonstrated that we can imprint a phase. So this is essentially the oscillation that I just shown you. If we go to the pi point and imprint the phase, we can see the oscillations. Like these are the ingredients. We haven't seen any plaquette coherences yet. So this is something that we are still working on, but we can already implement the individual X and Y pulses in order to look for them. And so I think what I really like about this is that it's a way to non-adiabatically prepare this kind of spin liquid puddle, if you want to call it like that. And we can now do this with very large systems. And with this, yeah, I just want to show you this conclusion slide. So essentially, we have been working on this analog Hamiltonian engineering side of things where we implement topological models and these dimer models. And we are adding all these digital control elements in order to extract more complex observables. And with this, I would also like to thank in particular the cesium team, specifically Simon, who is leading the study, Irene, Sungjung, and Alex, who is now at eCookie. And yeah, they have been working very hard on this problem. Thank you.
Very basic confusion about your Gauss law representation in terms of monomers and dimers.
Okay, let me go back. Right, so what's the easiest? Let me go back to the Hamiltonian first, maybe. Let me go back to the Hamiltonian.
So this is U1 and 2 plus 1, right?
Yes.
Okay.
Yes.
Yeah.
And you only have these processes, right, that are allowed. And so if you play this game, I mean, you immediately find that the only configurations that are allowed by Gauss law, I mean, as in the typical dimer models, that's what you typically get, that each vertex can only be connected to one dimer, which are these 4 configurations. But we also include the monomer dynamics. So the all monomer state would be like the green occupied site on the vertex.
So what's a monomer? I'm very confused by what a monomer is in your representation. I think in terms of, like you're matching fluxes, right? But in principle, you can have large fluxes.
Well, it's also a truncated model, right? So if you actually think about a different mapping, which we can also do, which would be the one down here. So that's the typical U1 QED mapping. Then you can assign arrows to the different electric fields. And the dimer would be actually a large, so this is the spin ice language. A dimer would be a large +3 electric field connecting like a positron and an electron. It's an equivalent mapping, just now in the language of dimers and monomers. And monomers, just if you break up a dimer into 2, generates 2 monomers.
So my question is how, I mean, this is interesting in its own right, but I mean, is this really U1 QED? Because you're doing some significant truncation.
I think that's the interesting question. So
Yeah.
it's U1, it has the same symmetry, but it's heavily truncated,
Right.
and it will not share all the phenomena of QED.
Right.
It's a very simplified
Right.
quantum link version.
Right.
And it's really more, I think, the dimer model
Right.
physics that one finds.
So can you think about this in this Rishon language? I mean, can you think about dimers in terms of combinations of Rishons?
Yes. Yes. Right, so the Rishon side in this case would actually be the dimer,
Yeah, okay.
where we have the two particles,
Okay.
which you can split into the two Rishons. Yeah.
And you also deal with fermions.
Very good point. So we are actually gearing up to do that. So for the moment, everything is boson, but we do want to realize this with fermions. It's a bit, I think it's an interesting question to even understand what the fermionic statistics in this highly constrained model will give you. And yeah, I don't know, but that's one of our main goals, to actually do this with fermions.
Would it also be possible to use optical lattices for non-abelian, like SU2?
Very good question. We have been working on this too. It also connects to our fermionic platform. What we are trying to do there is actually by hand put singlets onto the 2D lattice, and then you can cook up correlated hopping terms where you stay within the singlet subspace. This gives you a SU2 symmetry. We have worked it out in 1D. I mean, it should also work in 2D, but it's hard. Yeah, I think I know how to do SU2, but doing something more complicated, not yet.
There are no results. As in, there are
No. But we now have our microscope online, so we have single atom images of our fermionic atoms. So I hope that this we will be able to do soon.
I had a question too. So have you explored putting in boundaries and interfaces in the spirit of this program? Like do something to half your lattice and explore what happens on either side?
So not yet here. We have done this in the context of topology to study edge modes. So essentially we cut the lattice in half and block half of the sides to simulate the boundary, so to speak. And then we see chiral edge modes and the dynamics of chiral edge modes. Here we have not done any boundary type effects, but we are now, what we are planning to do, because this is actually quite nice for this type of constrained models. If you look at this system, it's very easy to generate boundaries, because if you start resonantly kicking out some of these atoms, it's a natural boundary. Like the system cannot explore it any further because there's no neighbor, so it cannot connect to anybody else. So you could also, if you cut out small systems, do very nice finite size scaling in this platform, because well, you just generated the different edges as you like and then scale it up.
I think we should probably end it there. There's coffee outside, I believe, and in about half an hour we can gather again for the gong show. But before we do all that, let's thank Monica.